Section 7.3 is on sampling distributions and the central limit theorem. And this section is going to be kind of theoretical. It's really the closest thing we're going to get to theoretical in this introductory course. But the consequences of the central limit theorem are extremely important to everything else we're going to do in this course. Because what we're working up to is the ability to take a sample from a population and make meaningful predictions about the population based on that sample. So imagine in the United States government, every 10 years they do a census, and that's where, I mean, it's a major undertaking. They're already talking about the one that's going to happen in 2020. You know, so it's a huge undertaking. They try to sample every single house, not sample, they try to get the population. They try to get to every single household in the United States and ask them a series of questions. Let's just pick one of them, let's say the family income. And so in the years between that, they still have to have a gauge as to, you know, how the economy is doing. They can't just do it every 10 years. So in the intermediate years, they'll do a sample. And so they'll maybe survey, I'm just making this number up because I don't know how many they survey, but let's say 100,000 households. It's probably way more than that. But let's say they survey 100,000 households and they ask them what their household income is. So imagine if they did that over and over again. So they first take a sample of 100,000 people and they get the average household income to be $40,000, let's say. And then they do another sample of 100,000 people. Very unlikely that it's going to be the same 100,000 people, so it's very unlikely that you're going to get the same average income from those 100,000 people. It might be, say, 41,000. And then survey another 100,000 people, and the average income for that sample might be 39,000. And so you're going to get all these different X bars. Remember, X bar is your sample mean. So you're going to have all these different sample means, and if we could find every single one of them, which of course is not possible, you know, in a country as large as the United States, there's no way you could get every possible combination of 100,000 households. But theoretically, if we could consider that a sample. So like you'd have X bar 1 from the first sample of people that were surveyed, and then X bar 2 for the second sample, and X bar 3 for the third sample, and all the way up to, I don't know how many there would be, billions and billions, but we'll say X bar n for the last sample. If you could think of that as a distribution in and of itself, that's called a sampling distribution, and it has some very, very important consequences that make everything else that we're allowed to do in statistics, makes everything that we're about to do, makes us allowed to do it. So I took this example from the book, and it's kind of hard to see when I'm talking in such broad, huge terms like everyone in the United States and a sample as large as 100,000. So let's do it on a really small scale, just so you can see the consequences from this. So what we're going to use for an example of a sampling distribution is we're going to use a tetrahedral die. Now that's a four-sided die. It's used often in games like Dungeons and Dragons, but other games too. And they're shaped like a pyramid, and so it has 4 faces with the numbers 1, 2, 3, 4. And so it's just like a regular die, except for instead of 6 sides, it has 4 sides. And so if we wanted to get the population mean and variance and standard deviation using the techniques we've used before, notice that the mean, well, you would just add up all the possible outcomes. You're either going to get a 1, 2, 3, or 4 and divide by the total number of outcomes. So mu, is 2.5. Okay. Now the population variance, we don't use that so much, but you can see that they're doing it by hand, using the formula for the variance, which is each outcome minus the mean squared, and you add those up and divide by the total number. that gives you the variance, which is 1.25, but it's the standard deviation that we usually work with, and that's the square root of that, so it's 1.118. Okay, so that's for all of this that we're talking about right here is for the population. Notice our use of Greek letters to represent it. We know it's a population because we're looking at every possible outcome, which are the numbers 1 through 4. Now we're going to start taking samples from those. So imagine tossing the die 3 times. So we're taking a sample of just 3. The sequence of 3 numbers that is observed is a sample of size 3. So we're taking n equal to 3. That's our sample size. And notice there are 64 possible outcomes. The reason that is imagine that you're tossing the die 3 times. We'll do that good old slab method that we learned about before. We're tossing the die 3 times. And so the first time we toss the die, there are 4 possible outcomes. It can be repeated. The next time you toss the die, there are 4 possible outcomes. And the third time you toss the die, there are 4 possible outcomes. So there's 64 total outcomes. That's where that number is coming from, 64 possible samples. And they're all equally likely. And so what they did, and luckily we don't have to do that ourselves, is they got every possible outcome. So those are the samples right here. This is every possible combination of 3 taken from the numbers 1, 2, 3, 4. So here's all 64 possible samples. And then what they did is they averaged that sample. So notice like this first one, they found the mean of that sample, and they're calling it x bar because it's a sample mean. So they took the 1 plus 1 plus 1 and divided it by 3. Then for this one, they took the 1 plus 1 plus 2 and divided it by 3, and so on. And so they calculated the sample mean for every single possible sample out there. So those are the numbers that are in the, I'll just highlight those in green. Those are your sample means. Okay, and so then what we're going to do with these sample means, so we have 64 sample means, 64 x bars, and so what they're going to do with those sample means is consider that a distribution. So our distribution is now x bar 1 all the way up to x bar 64. And so we're going to find the mean of all of those x bars. And that's what they do next. So they're explaining it some more here. It says the columns labeled x bar contain the values of the sample mean for each of the 64 possible samples. Some of these values appear more than once because several samples have the same mean. So like notice here where they took like for example 144 and got a mean of 3, that's going to be the same thing as 441, a mean of 3. But that's okay, they can repeat like that. And the mean of the sampling distribution is the average of these 64 values. So if you were to take all of those 64 values, the x bar 1 plus x bar 2, all the way up to x bar 64, let me write that down. You're taking x bar 1 plus x bar 2, all the way up to x bar 64, and you divide that by 64, that's what we call the mean of the sampling distribution. And the symbol for that is mu sub x bar. And it turns out, look at what it turned out to be. Now, I'm not going to do the actual calculation. 64 is a lot of numbers. It's a big sample. But notice it turned out to be 2.5. Now, go back to our original population mean, Notice that was also 2.5. It will always work out like that. And I'm going to summarize everything in a minute. But the mean of the sampling distribution is always equal to the population mean. So in other words, mu sub x bar is always the same as mu. Now let's talk about the standard deviation. Notice for the population, it was 1.118. So they recalculated the standard deviation. This is, I think, a typo. It should be called sigma sub x bar. Notice it's not the same. It's 0.6455. Well, it turns out that we get sigma sub x bar, and again, I'll summarize all this in a second, but we get sigma sub x bar by taking sigma, the original population standard deviation, and dividing it by the square root of your sample size. So in this case, it's going to be that, what was the original standard deviation? 1.118. And we're going to divide that by the square root of 64, which is 8. So notice if I take that 1.118 and divide that by the square root of 64, which is 8, we get the we get something wrong. What am I doing wrong? Oh, I'm making a big mistake. Let me go back. The square root of n is correct, but n is not 64. Sorry about that. If you go back, I even wrote down what n was up here. N is 3. So we're going to divide that by the square root of 3. You're dividing by the square root of your sample size. So that's 3. So sorry about that. So we're going to take the 1.118 and divide that by the square root of 3, which is 0.6455 or 0.645, like they have stated. Or no, they have 0.6455. And so you can see that's how we get this. Okay, and these relationships hold true in general. So not just for this example. The standard deviation, sigma sub x bar, oh, this is just one other thing. It's sometimes called the standard error of the mean. It's sigma sub x bar. So let me just summarize what we saw here. We saw that if we let x bar be the mean of a simple random sample, of size n, drawn from a population with mean mu and standard deviation sigma, then we have these consequences. The mean of the sampling distribution is called mu sub x bar, and it's just equal to mu. So the mean of the sampling distribution is the same as the mean of the population. And then the second consequence is that the standard deviation of the sampling distribution also called the standard error. Is sigma sub x bar, and it's equal to sigma divided by the square root of n. Okay, so let's look now at the central limit theorem, which summarizes this even more, because what we're going to be doing, like we're getting ready to do confidence intervals and hypothesis tests. Those are both ways to make inferences about the population. They're all going to rely on the fact that we have a normal distribution. That's going to be really important to this, and that's what the central limit theorem allows for. So the central limit theorem says if we let x bar be the mean of a large simple random sample from a population with mean mu and standard deviation sigma, then x bar has an approximately normal distribution with mu sub x bar equal to mu and sigma sub x bar equal to sigma divided by the square root of n. So basically what this is telling us is if we have a large sample, then we are guaranteed that x bar has a normal distribution. No matter what the population distribution was, x bar will be normal as long as your sample is large. And so this word large is not a judgment call. Large has a number assigned to it, and it's that n has to be greater than 30. So 30 is the magic number between a large sample and a not large sample. So as long as your sample is larger than 30, you're guaranteed that the distribution of the means is going to be normal. Now, so just to kind of summarize this, to kind of take it down to what's important. If your sample is bigger than 30, x bar is normal regardless of the population distribution. You don't even have to look at what the population distribution was if you have a sample bigger than 30. Now, if your sample is less than 30, which that's going to happen sometimes in real life, we prefer large samples. They're better. But, you know, if you're studying some sort of maybe very rare disease, you might not be able to get a sample bigger than 30. X bar is only normal if the population is normal. We'll say the underlying population. So the population that you're taking the sample from, if it's normal, then x bar is normal regardless of the sample size. So another way to say that is if the population is normal, small samples are okay. Let's say sample size doesn't matter. And then if you don't know if the distribution, so if you have a small sample And if the distribution of the underlying population is not normal or unknown, we cannot assume the sample is normally. We cannot assume X bar is normal. And so you would have to use other methods, which we won't get into in this class. So if we come across that scenario, we'll just say we can't do the problem. So we're focusing only on ones where we can apply the normal distribution. But you do have to know when you can apply it and when you can't. Okay, so let's look at how this all comes into play with examples. So a lot of that has been very theoretical, and hopefully you followed what I was going through. But in practice, you should still be okay, even if it seems still a little strange to you. So let's look at some examples. So on page 315, we're going to look at number 12. And it says a sample of size 284 will be drawn from a population with a mean of 45 and a standard deviation of 7. So some important things about this is we're taking a sample size of 284. The mean is 45 and the standard deviation is 7. Find the probability that X bar, notice how it's an X bar, will be greater than 46. So let's write that out. So we want to find the probability that X bar is greater than 46. Well, notice that they didn't tell us anything about the distribution of the population. Nowhere in there does it say, you know, a sample was drawn from a normal population. But we don't care because look at how big our sample size. It's 284. So that's much bigger than 30. We know that X bar will be normally distributed, and that's what they're asking about. So what they're wanting us to find, just like we were doing before, but we're going to do it for X bar instead of X. Here's the mean at 45. We want to find the probability that X is greater than 46. So 46 would be about right here. So we're looking for this area I'm about to highlight. So we want to find this area right here. Okay, so we're going to do that. Here's 46. We're going to do that just like we were doing before. We're going to use the normal CDF. And remember the order that we put in numbers. We have the left bound, the right bound, the mean, and the standard deviation. But notice that since I'm doing this problem with an X bar, that my standard deviation is going to be mu sub X bar. My mean's actually going to be, sigma sub X bar. And my mean's actually going to be mu sub X bar, but that's not as critical because mu sub X bar is the same as mu. But sigma sub X bar is going to be our regular sigma divided by the square root of our sample size. That should be 284. So if you have an X bar in your problem, you've got to have a sigma sub X bar in your calculation. So for this problem, it'll be the normal CDF. The left bound is 46. The right bound, well, it's going on forever. It's infinity, but we use the 1E99. The mean is 45, and then the standard deviation is 7 divided by the square root of 284. And you can just type it all in like that. And so that will give us this probability. So we're going to go to second bars, number 2. And we had 46, 1E 99, 45, and then 7 divided by the square root of 284. And just make sure you come out or end your square root before you end the parenthesis on the normal CDF. And so we get 0.0080. That would be the probability. Notice that it's very unlikely. It would be very unusual. It's less than 1% chance that this would happen. Now, just as a contrast, imagine that we were just selecting one from the, well, never mind, because we don't know that this population is normal. We can't do that. I'll illustrate that later. Okay, then for part B, they want us to find the 75th percentile of X bar. So what they're wanting us to find, so here's our distribution of X bar, which we know is normal because our sample is big. Here's the mean at 45. We want to find that value of X bar, wherever that might be, so that we have 75% of the area below it. That's what the 75th percentile means. So we want this area to be 0.75. It's the same thing as asking us to find Q3 for X bar. So remember, when you know the area and you're looking for the value on the axis, you use the inverse normal. And we put in the area to the left, mu, but now it'll be mu sub X bar, and sigma, but now it'll be sigma sub X bar because we're finding the 75th percentile of X bar. So this will be the inverse normal the area to the left is 0.75. The mean was 45. And the standard deviation will be 7 divided by the square root of 284. And so that will give us the 75th percentile. So let's go ahead and calculate that. So second bar is number 3. And we have 0.75, 45, and 7 divided by the square root of 284. And so that gives us 45.28 would be the 75th percentile. Okay, let's look at another problem. This one will apply to a real-life problem. So it says the National Health and Nutrition Examination Survey reported that in a recent year, the mean serum cholesterol level for U.S. adults was 202 with a standard deviation of 41. The units are in milligrams per deciliter. A simple random sample of 110 adults is chosen. So notice that N is 110, mu is 202, and sigma is 41. What is the probability that the sample mean cholesterol level is greater than 210? So it makes a big difference if you're doing a distribution with X or if you're doing a distribution with X bar. So you need to pay really close attention to the wording. Right here it says sample mean cholesterol. That's what's telling me that it's X bar. It's a sample mean. And so we want to find the probability that X bar is greater than 210. They do not tell us that serum cholesterol levels are normally distributed, but we don't need to know that because our sample is large. It's bigger than 30. So I know that X bar will be normally distributed regardless. And so here's the mean at 202. 210 is going to be to the right of that. And we're looking for this area right here. So we'll use the normal CDF. Left bound is 210. Right bound is 1E99. Mean is 202. And then for the standard deviation, we're going to take 41 and divide it by the square root of 110. Because remember, whenever you have an x bar in your probability, you're going to have to use sigma sub x bar in your calculations. And how we knew to use an x bar in our probability was these words right here, sample mean. Okay, so let's do that calculation. So, second vars number 2, we had, already forgotten the numbers. Let me find this problem. So, the mean, or the left bound was 210. The right bound was 1E99. The mean was 202. And the standard deviation will be 41 divided by the square root of your sample size, which was 110. And so that's equal to 0.0204. .0204. So that's the probability of finding a sample of 102 people and that sample having an average greater than 210. Okay, let's look at part B. What is the probability that the sample mean cholesterol level is between 190 and 210? Well, again, notice how it says sample mean. So we're looking at x bar. So this is a distribution of x bar. Population mean is at 202, and we're looking between, which is the same as the sample mean distribution, and we're looking between 190 and 200. So we want to find the probability that it is in this region. So we're looking at the probability that x bar is bigger than 190 but less than 200. So that'll be the normal CDF. The left bound is 190, the right bound is 200, the mean is 202, and then the standard deviation needs to go with x bar, so it's going to be the 41 divided by the square root of 110. And so if you calculate that, go ahead and try it on your personal calculator. I'm going to do it on my handheld one. And we get 0.3034. Would be that probability. And then finally, for the last question for this one, would it be unusual for the sample mean to be less than 198? So remember, for unusual, what you're going to have to do is calculate the probability that x bar, and I'm using x bar because of these words sample mean, is less than 198. So we're going to calculate that, and then if it's less than 0.05, then it's unusual. So here's the mean at 202. 198 is going to be to the left of that. And we're looking at this area right here. So this will be the normal CDF. Left bound now is negative infinity, so negative 1E99. Right bound is 198. The mean is 202. And again, because I'm using x bar, I've got to use sigma sub x bar, which in this case is 41 divided by, was it 41? Yeah, 41 divided by the square root of 110. So let's look at that one. So we'll have second vars, and actually, no, that's okay. Second vars, number 2. So negative 1E99, 198, 202, and 41 divided by the square root of 110. Come out from under the square root, or if you have an 83, you'll have to close your parenthesis on the square root and then close the parenthesis on the whole thing. And so we get 0.1531, which is not less than 0.05, so this is not unusual. So it wouldn't be unexpected to take a sample of size 110 and have the sample mean cholesterol level to be less than 198. Okay, let's look at number 24. Number 24 says the College Board reports that in 2013 the mean mathematics SAT score was 514 and the standard deviation was 118. A sample of 65 scores is chosen. So let's just summarize what's important. N is the sample size. That was 65. So notice it's large. It's bigger than 30. The sample or the population mean was 514 and the population standard deviation was 118. Okay, and so for part A, it says, what is the probability that the sample mean score is less than 500? So again, it's this word right here, these words right here, sample mean. That's how I know when I do the probability to write X bar. And we want that to be less than 500. And so if you're using X bar, then you know that you have to use sigma sub X bar in your calculations. X bar is going to be normally distributed because we have a large sample. Here's the mean at 514. So we're looking at less than 500, which would be on this side. So we're looking for this area right here. So this will be the normal CDF. The left bound is negative 1E99. The mean is 500. The standard, I'm sorry, let me say that again. The left bound is negative infinity, negative 1E99. The right bound is 500. The mean is 514. And then the standard deviation is going to be the sigma divided by the square root of n. So it's that calculation in there that's often forgotten. Because I have an X bar and my probability, I've got to use sigma sub X bar in my calculation, which is sigma divided by the square root of n. Okay, so let's do this calculation. I switched my calculator so it'll look more like those of you that have an 83, just so you can see the difference. So if we go into second vars number 2, my left bound is negative 1E99. My right bound is 500. My mean is 514. And then my standard deviation is 118 divided by the square root. And the main difference is your square roots look like this if you don't have the math print option on your calculator. 65, so I just wanted to show you the difference. You're going to have to close that parenthesis on the square root and then close the parenthesis on the whole thing. And so we get that probability to be 0.1694. So that's the probability of taking a sample of size 65 and getting a mean that is less than 500. Okay, Let's do another one. Part B, what is the probability that the sample mean score is between 480 and 520? So we're looking for the probability that X bar is between 480 and 520. And again, this is so important. I'm using X bar here because it says sample mean. That's the only time that you're going to do this where you divide by the square root of n, is when you're doing this for a sample mean. So we're looking at this distribution of X bar. Here's the mean at 514, and we're looking between 480 and 520. So we'll use the normal CDF. The left bound is 480, the right bound is 520. The mean is 514, and then again you're going to do 118 divided by the square root of 65 because we're dealing with X bar. And for this one you should get, I'll let you calculate it yourself, but you should get 0.6490 is that probability. Okay, then for part C, they want us to find the 80th percentile of the sample mean. So we're looking for a value of X bar because, again, sample mean, but we want that value of X bar so that 80% of the values are below it. So here's the mean at 514. We're looking for this X bar, whatever it might turn out to be, so that this area down here is 80%. So remember, when you know the area and you're looking for the value of X bar, that's when you use the inverse normal. So we'll have the inverse normal, the area to the left is 0.8, the mean is 514, and again, because we're doing a value involving X bar, we've got to use for our standard deviation sigma sub X bar, which is sigma divided by the square root of n. So in this case, it will be 118 divided by the square root of 65. And again, I'll go ahead and let you calculate that on your own. You should get for X bar 526.3. Okay, would it be unusual if the sample mean were greater than 550? Well, anytime they're asking you a question about unusual, you have to calculate the probability. And again, notice sample mean. So we're looking for the probability that X bar is greater than 550. And so that's how we decide if it's unusual or not, is if it's less than 0.05. So calculating this, here's our distribution of X bar. Here's our mean at 514. 550 is going to be up here somewhere. I don't know where yet because we're going to calculate that area and see if it's unusual. So this will be the normal CDF. Notice we know the value on the axis. We're looking for the area, so that's normal CDF. Left bound is 550. Right bound's 1E99. The mean is 514. And the standard deviation is 118 divided by the square root of 65. And I don't have that number in front of me, so let's calculate it. So second var is number 2, and put your values in. Okay, and we get 0.0070 when you round to 4 decimal places. And so if we decide if that's unusual or not, notice that it's less than 0.05. So that tells us that it's unusual. Okay, so for the last question on this one, it says, can you tell whether it would be unusual for an individual to get a score greater than 550? Explain. Well, this is going back to the theory of it all. We're looking at an individual. So they're asking us, what they're asking us is, could we calculate the probability that X is greater than 550? So the question is 550. Can we make this calculation? Well, remember, everything that we do here is based on the normal distribution. Over and over again, we're drawing that normal distribution. So if we don't know what we're calculating has a normal distribution, we can't calculate it. So with all of these questions A through D, we were dealing with X bar, and we know that X bar has a normal distribution because of our sample size. It's bigger than 30. That's the central limit theorem. But if you look at the statement of the problem, which is up at the top of the screen, nowhere in there do they tell us that the population is normal. And so when we go down to this last question, for an individual, we would have to have a normal population, and we don't know that we do. And so the answer to this question is no, because we don't know if the population is normal. Now, if we knew that, then we could make this calculation. That would be like what we were doing in the previous section. But we don't know that the population is normal, so we can't make that calculation. All right, I have one last example. I believe this is the last one, to look at. And it deals with an elevator. And it says, engineers are designing a large elevator that will accommodate 40 people. The maximum weight the elevator can hold safely is 8,120 pounds. According to the National Health Statistics reports, the weights of adult U.S. men have a mean of 194 pounds and a standard deviation of 78 pounds, and the weights of adult U.S. women have a mean of 164 pounds and a standard deviation of 77 pounds. So let's summarize that. So for men, mu is equal to 194. And sigma is equal to 68. And for women, mu is equal to 164, and sigma is equal to 77. Okay, and so we want to answer some questions. So if 40 people are on the elevator and their total weight is 8,120 pounds, what is their average weight? Well, if we have 40 people on the elevator, to get their average weight, we're going to take the total weight divided by 40. So the average weight will be the 8,120 divided by 40. And so that gives us 203 pounds. So that would be the average weight. So what they're saying here, notice that the maximum weight on the elevator for safety reasons is 8,120 pounds. So we're finding out the average weight of each person if the elevator was full. Okay, so that means that on average, each person can't weigh more than 203 pounds, or we're going to exceed the weight limit. So if a random sample of 40 adult men ride the elevator, what is the probability that the maximum safe weight will be exceeded? So they're asking us to find the probability that X bar is greater than 203 when we have 40 adult men on the elevator. So 40 is bigger than 30, so we have our normal distribution for X bar. Here's the mean at, let's see, for men it's 194. So here's X bar at 194, and we want to find the probability that it's greater than 203. So we're looking for this area right here. So this will be the normal CDF. Left bound is 203, right bound is 1E99. The mean was 194. And then we're doing this for X bar, so the sample standard deviation, or the population standard deviation was 68, and we're going to have to divide that by the sample size of 40. And so we should get, what number is this, 28. So we should get 0.2013. Okay. Now for part C, if a random sample of 40 adult women ride the elevator, what is the probability that the maximum safe weight will be exceeded? So if it's all women, what's the probability that X bar is greater than 203? Okay, so for women, the mean was 164 pounds, I believe. Yeah, 164. And we want to see the probability that it's greater than 203. You can see it's going to be smaller because we're starting off with a smaller average weight anyhow. And so this will be the normal CDF. The left bound's going to be the 203, the right bound's still 1E99, but now the mean is 164, and the standard deviation was 77, and we're going to divide that by the square root of 40, the sample size. And that, if you do that calculation, you should get 0.0007. Let's do that one together because I think it's going to be something that I want to show you. So if we do second vars number 2, we have the right bound, which is 203, the left bound, which is 1E99, the mean, which is 164, and the standard deviation, which is 77, divided by the square root of 40. And so, yeah, I just wanted to remind you of this. When you get that E, notice that we have 6.7. You can't have a probability bigger than 1. So that tells me I need to read on down the number, and it's actually E to the negative 4. So we're going to have 3 zeros before we even hit this 6.79 or 679. So in other words, we have 6.79 times 10 to the negative 4, which if you convert that to a decimal, it's going to be 0.0007. So it's very unlikely that if it's all women on the elevator that the maximum weight will be exceeded. It wouldn't be that unusual if it was all men on the elevator. Okay, and that finishes up section 7.3.